Hello everybody, we're going to start our discussion on section 2.7 with a discussion about sets and set notation, a very important topic to understanding the rest of the section and what we're going to be dealing with later when it comes to solving inequalities and other similar things. So in this presentation, all I want to make sure you have on board is the following objectives. I want you to be able to write a set using the listing method and SetBuilder Notation. Those are two of our basic kinds of notation that we use. We want to know when one set is a subset of another. We want to be able to join sets through a union or intersection of sets, be able to use inequalities in sets, be able to graph sets using the number line, and be able to write sets of real numbers using interval notation. That's the third kind of notation that we use when it comes to dealing with these kinds of sets. Okay, so the very first thing here is just to list through a few definitions that you guys are definitely going to have to know, and please make sure you take a look at these in the textbook and write them down. When we say a set, we mean a collection of objects, such as numbers, letters, or ideas. A set can contain anything, but those ideas, numbers, or letters are very often joined by some property or some pattern. An element is each object contained in the set. So if we have a set that contains our counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, each object, the number 1, the number 2, the number 5, and so on, are elements of that set. A subset is a set that is made up of objects taken from a larger set. So if I told you all of the counting numbers from 1 to 5, 1, 2, 3, 4, 5, this would be a subset of the set of all counting numbers. Another idea that we often use in mathematics is something called a null or empty set. If you currently write zeros with lines through them because you're a previous Navy and you write that in the log books, I'd like you to get used to the idea of seeing that symbol being used for the empty set, or the set that contains no elements. We also have a symbol that represents the element of. So when we want to indicate that one item is an element of a set, then we use that little sideways looking U with a line through it. Almost looks like an E. If we say that something is not part of a set, we just put a line through it, kind of like a no smoking sign. This is a symbol that means is a subset of. We will probably not run into this quite yet, but later on in our studies we might. So just so that you know, this last symbol means is a subset of. Some more definitions. Whenever we have two sets and we want to join the elements of the two sets together to make a larger set, we use something called the union of the two sets. The union is represented by the symbol that looks like a U, maybe more elongated or drawn like a cup, maybe if you think about it. The other way of joining two sets is something called an intersection. An intersection is used to join all the elements in one set containing one set with elements in another set. Now, if the sets have no elements in common, we call that a disjoint set, and I'll illustrate these in a moment. Now, in order to use these symbols, we will want to get into understanding how do we define a set. What is one way of writing a set? Well, one method is called the roster method, or the listing method. In this method, we simply list the elements one by one by one for all the elements in the set. So we say whatever element 1 is, comma, whatever element 2 is, comma, and so on. By the way, when you see the little dot, dot, dot at the end, that is called, and that symbol is called an ellipsis, and it means a continuation of the set following whatever pattern has been shown by the elements in that set. So let's take an example right here. We've got two sets that I've written in the roster method. So set A is the set 2, 3, 4, 5, and 6. And set B is the set 4, 5, 6, 7, and 8. And we're interested in answering the questions, oops, page up, what is the union of set A with set B? And what is the union of intersection of set A with set B? So let's take on our union here first. Our union is going to be a set that is formed by joining all the elements in set A and all the elements in set B, but we're not going to repeat elements. So we notice, for example, right here that we have to include 2, we have to include 3. We definitely have to include 4, 5, and 6 as they're common to both sets, but we're not going to repeat those numbers. And then we add 7 and 8 on the end. We call that the union of the sets A and B. It's a larger set than either set, but it contains all the elements contained in each of those sets. Now the second one is an intersection. It's a little bit more exclusive a club right here. What we're looking for is, well, what elements do both of these sets have in common? Well, we see that set A has 2 and 3, but that's not in set B. 4, 5, and 6 are contained in set B, but 7 and 8 in set B are not contained in set A. So our intersection of the sets A and B is given by the set 4, 5, and 6. Right? So an intersection is a much more exclusive type of set. It's what points or what elements do the two sets have in common, whereas a union includes all of the elements in both sets. Another way of writing sets besides using the roster method is something called SetBuilder Notation. SetBuilder Notation can be used with both countable and uncountable sets, and there are sets that we just cannot go through and explicitly count every single element one by one by one. So instead we use this notation, and you see that right here we have 2 curly brackets on the outside, and we say X, and that's going to indicate X is an element. We read this bar to say such that, and then X has some property that all the elements have in common. So the variable X is represented to indicate any, and therefore all of the elements in the set, and the property is the shared element that makes all these items well defined. So let's talk about an example of this sort. Let's say that I told you I had the set A, which was the set of all, where X was the set of all X greater than 5, and X was in the set, is an element of the set of real numbers. And oppose that to X such that X is greater than 5, and X is in the set of integers. Well, first of all, we might ask the question, what's the difference between these two things? Well, recall that the set of integers is the set of all positive or negative whole numbers. So, for example, if I said 6, 7, 8, 9, or so on, that could be an indication of my set B with only integers in it, right? So in the roster method for set B, we might actually see it written out as the numbers 6, 7, 8, 9, and so on. Right? These are our integers. Now, unfortunately, we can't do that with all the real numbers greater than 5, right? Because if we talk about numbers that are greater than 5, well, we could mean 5.0001. We could mean 5.73. We could mean 5.21. We could mean 6, but we could also mean 10.17189743, an irrational number, right? There's all kinds of numbers that fall in this set of real numbers, so it's impossible to list A. So A cannot be listed. Okay. So the only properties that all of the numbers X have in common in this set is that they are real numbers that are greater than 5. All right, so that's our difference between these two. First of all, not everything can be listed, nor should we expect that to happen. So if we see this set right here, we see in SetBuilder Notation all x such that x is greater than 5. What do we assume, do you think? Well, the answer here is that we assume the first thing. We say that if we don't see any other indication in our set, we must assume that if no other indication is given, the set of all x such that x is greater than 5 means the set x over the set of real numbers. So just like our set A right there, that is another way of writing set A. All right, so let's see what this looks like on the number line. A couple of symbols so that you know when you see a greater than symbol or a less than symbol, we're going to use a rounded bracket. I know that in some algebra courses they use open circles and closed circles, but we're not going to do that here. We're going to use a round bracket here. We say all x greater than 0. So if we don't want to include 0 in this set, we're going to put a round bracket there to represent that. And then we're going to draw or darken in our number line to represent the fact that this set contains all of the values greater than 6. I'm sorry, greater than 0, including all the whole numbers, 1, 2, 3, 4, 5, 6, and so on, but every single number, whole number, rational number, irrational number in between each of those values. So we want to make sure that we include them all, so we darken in that number line to represent that. How about this one down here? Well, anytime we see the square bracket, that means we're going to include the endpoint. And so if we're going to include the endpoint right here, we're going to say that in this case we're going to use the greater than or equal to symbol. And so we're looking at this set and we say, all right, looks like the endpoint right here is at -3 and goes off to the right. So how should we indicate that? In our SetBuilder notation, we're going to write a curly bracket. We're going to indicate the letter x to represent a generic element within our set. We're going to write a vertical bar. That vertical bar, by the way, again, is read as such that. So whenever you see that vertical bar, you say, this is read all x such that. And then we get a shared property. Well, what is the shared property? It looks like it's the set of all real numbers greater than or including -3. -3, pardon me. And then we close off that bracket. So we're saying all x such that, and of course by the rest of this, we're indicating that we want all real values greater than or equal to -3. So that's our notation right here for that set builder. Very important to us.